Hey folks, so today we're going to be doing some Newton's Law demos. And hopefully at this point you've gone through, you've taken the notes, you were in class, or you've at least kind of watched the video or taken the notes of it. And for today we're going to be doing 12 demos. Hopefully 12, I actually might not be able to find one of them. But you will need two pieces of paper, one of them set up with Newton's Law demos part 1, split it down the middle, and then kind of did a cross and a cross. We have 6 here. Did the same thing on another page. And so there, that's kind of it. And so the first demo is called the old cup and coin. And I have a cup, and I have a card, and I have a coin. And so really all I'm gonna have you do with all the demos, every single one of these demos, you need to diagram it, and you need to explain it using one or more of Newton's laws. That's it. That's all you got to do. If you see it through the lens of the first law and you can explain it the best that way, perfect. If you can kind of see it through the lens of this third law, then add that to kind of as space permits, all right? So the cup's here, and this is the first part of the demo. Now the second part of the demo is, right? Pretty exciting stuff, I know. But wait, there's more. We could, in fact, do it that way too. And so that's it for our first demo. And so really you can pause right here, sketch it, explain it. Now, as an example, because I wanted to just show you kind of what we're looking for here, what my expectation is, something like this. So I have a little sketch, and then I've gone and I kind of explained it actually in the terms of the first law and the second and the third, because I kind of could see all three with this, okay? Okay, so demo number 2 here is the old broom and pie tin. So what I'm going to do is I'm going to use this broom to get all 3 of these golf balls in all 3 of these cups at the same time in about 1 second flat. So sit back, enjoy, and a 1, 2, 3. Ta-da! Okay, so demo 3 is called Walking on Sunshine, but only in the case where sunshine is glass. Now, this is not polished glass. You can see this is actually part of like a measuring cup. There's some other kind of measuring equipment here that just kind of breaks in our chemistry classes, essentially. And so this is kind of an interesting one. The glass is sharp. I will tell you, it helps that the glass is pretty thick. And so we sit down, we kind of gently put our feet in, all right? And then just nice and casual like, kind of just stand up. And that's really it. There we are. You can kind of bounce around a little bit. And so that's it, walking on sunshine or glass. And the trick is make sure that you wipe off all the glass from your feet. If you were to step on that same shard out here on the tile, you would get cut. Hey folks, so I've got my tablecloth here. And with this fourth demo, I think, or I'm not sure which number we're on now, it's the tablecloth trick. And so I'm not getting ready for lunch. What I am, in fact, doing is getting ready to kind of do a demo that relates to Newton's laws still. So hopefully we're sketching each of these. We're kind of going about and trying to then, after a brief sketch, doesn't need to be the Mona Lisa, we're then really kind of trying to go through and explain it using 1 or 2, maybe all 3 even, of Newton's laws. So the trick with this guy is that you want to make sure that you pull straight down with it. You're not like rippling a bed sheet or something that ends up making like forks go flying towards people's eyes. But it's pretty simple. So on 1, 2, 3. This demo is called green carts because I have these 2 little green carts. And the neat thing with them is one of them has a little silver button here on top. And when I push the button, this little thing kind of kicks out and it kind of pushes because there's actually a little spring underneath here so we can just kind of reload it. Now the funny thing is whenever we're using these, because we'll use this later in a momentum unit, we'll actually have these collide in 10 different ways and we'll kind of do presentations on it, I hope. is that these kind of tell something funny. So when I flip it, you can see that it already kind of tells us something important about our classroom. And it says that my countertops are not level, they're not flat. And so I can kind of put it this way, you can kind of see in this direction. So really that way and towards me are downhill. And so I want to try and make sure that whenever I'm not using these, I flip them this way because they're expensive, and if they fall, they get damaged. So with that in mind, I'm going to take both of these and I'm lining up so the little kind of punch part is right there. I'm going to put both kind of right at the 50. And again, I'm just going to have you watch, kind of do a quick little diagram, and then just explain using Newton's laws. Now, the neat thing is I have these blocks. And so this card's 200 grams, this card's 200 grams, this block is 200 grams, and this block is 200 grams. So really, if I put this right here, now this cart has twice the mass of this cart. So this is 400 grams, this is 200 grams. Okay, and then I go over, and I'm gonna line these both up so they're right at the 50. And all I'm gonna do is I'm just going to push the little button here with the block, so I don't bump it really in any other way. And we'll kind of just see what happens as the two fly apart. So 1, 2, 3. Okay, and I stopped them at about the same time. I'm not perfect, I know. But this one traveled 22 centimeters, and this one traveled right around 40 centimeters. So this one traveled farther, almost twice as far, but not quite twice as far. So I want you to just explain that using your knowledge of Newton's laws. What the heck is going on here? This one is not another Newton's laws demo, actually. I guess you could talk about the equal and opposite forces kind of at the point of contact here, or how it's staying at rest until a force acts on it, and then it stays that way until another force acts on it, I guess. But really, I wanted to look at these little birds here as a way of kind of talking about center of mass, because center of mass is still kind of a weird abstract topic. And so the neat thing is that these little birds balance incredibly well. I have just a little mechanical pencil here, and if I'm careful enough, I can balance the bird pretty well kind of right here on the tip of the pencil. And you can kind of push down, and they kind of do little bobs and dances and such, right? Now, the reason for why it works is that right here, right directly below the beak, is the center of mass. And so there's actually a lot of fancy math that I'm sure someone did to make sure that the wings here and here go far enough forward that they actually bring the center of mass also forward. If the wings were going straight out, the center of mass would drop down towards the tail, and the center of mass might be right somewhere here around the belly or something like that. Even more so, you can see if you look kind of close that it's darker here and here because there's actually little weights in the wings to make sure that this part is the heaviest, so that again, the center of mass is right there on the beak of the bird. And so the bird stays there because that, in fact, is the center of mass. If the wings were made longer or if more weight was put here, then that center of mass would shift farther towards the head of the bird, farther forward this way, and you could have a center of mass that's kind of floating out in space. But that wouldn't be very exciting because then I couldn't set that on it. It's actually the same reason why fidget spinners work. Kind of old and annoying as they are, they're kind of a neat thing because you're holding it right there on the center of mass. So that even though it spins, it's not like wobbling and kind of doing anything weird. It just feels really clean. And that's why a lot of people for a while were kind of obsessed with these. So it's the center of mass, again, is why these work. So that's it for now. And this will kind of help us out with future problems, demos, equations, kind of things along the way. Hey folks, so normally we do this next demo with a student and me, but due to current kind of coronavirus conditions, here is our student today. So our student's gonna go right here on this box of glass on this to be hopefully once motorized skateboard. And this demo is called Kick Push. And so typically, the student would have their feet kind of facing me. They'd be kind of doing the same thing mirrored. And so you put our feet together and we'll kind of kick off each other. Now, one thing I want to mention before we kind of do this one is our center of mass. And so in physics, we talk about systems a lot. And a system is really whatever the heck you choose to look at. If you're looking at just me and the skateboard, this system's center of mass, well, is somewhere right around here between me. if we're looking at the system of me on this skateboard and all of that, well, the center of mass is somewhere between the two of us because some of the mass is over there, but most of it's over here. So maybe the center of mass is at some point like, I don't know, maybe down here, kind of right in space, like actually outside of my body, okay? And so for the demo itself, though, we can kind of talk about the system of all of this together. And so the center of mass, again, is at some kind of spot between me, okay? So I'll kind of put my feet up here, and really I'm just going to kick off of our student here. Great. Hey folks, so what I have for this demo is called Threw It on the Ground. We have our 15-pound bowling ball, and which is right around 7 kilograms, and then our longboard, one of our 2 physics longboards. And all I'm going to do is throw it that way. And I just want you, again, explain. Use Newton's laws, quick sketch, easy little diagram, and then just explain it as best you can. So 1, 2, 3. That's it. This demo is actually 3 in 1. So the first version of this that you're going to draw and kind of explain is literally this as it is. We have a mayonnaise jar, but inside the mayonnaise jar, we have 2 pieces of string, and attached to the string up top we have a metal washer, as we can kind of see right here, and it's just hanging down. And then from the bottom we have a cork, and the cork is just kind of floating, doing its own thing. And so that's it. Explain this one using Newton's laws. Round 2 of the inertia jar is looking specifically at just the washer, but not when the washer is just being boring sitting still, but when I'm actually moving it. So I'll be pushing the jar this way, I'll be pulling it back, and in all the cases, I want you just watching closely, maybe rewinding, kind of playing it again, putting it at half speed, things like that, to just see what's happening with the washer and coming up with why that happens. You might want to do a couple freeze frame diagrams, so like in the beginning, and then when it's in motion, and then as it slows down, or something like that. And so I'll pull it back again now. Then we'll push it forward again, and then we'll bring it back. Final round, the hardest version of this, looking at just the cork. What is happening to the cork when I do the same exact things? So I'll push it to the left, that's forward for me, and I want you just watching the cork. And then I'll pull it back, and I want you again observing the cork and kind of seeing what the cork does kind of compared to the motion of the jar itself. And I want you just explaining what's happening, again, in terms of Newton's laws. So away, back, then away, and back. Now, there is a great video, I will say, by this guy called Smarter Every Day on YouTube, where he does something similar with a helium balloon and a regular balloon in a car. It would probably give you some good hints, or maybe even spoil it if you're stuck at explaining this. All right, here is, I believe, our last demo, and it's the pin board. You maybe saw some of these when you were little. There's all these little kind of needles or pins, but they're kind of nice and flat. And so if you put your hand on it and you flip, you kind of get this outlined impression of your hand. Now, the neat thing is I have one that's a real pin board. It actually has needles, very pointy little needles that would kind of stab into you. And I bet one of these, if you had just one, would kind of stab in and hurt. And so we can kind of see that it is a pretty pointy little mesh of needles here, and a couple like to stay up, unfortunately. But the neat thing is, since there are so many, this is kind of spoiling it, it works the exact same on my hand. I see this full impression of my hand. It feels a little different, a little odd, I will admit. And my hand is not just oozing blood all over the place. So that is our last demo, and I just want you to explain.